Hello, this is Bernie Ziegler, and this is a video of a recent talk that I gave at MITRE in Virginia on recent advances in the theory of modeling and simulation with implications for computational emergence. The talk is in two parts. First one is background on devs and the concept of closure and decoupling, and the other concepts we need to discuss the second part, which goes into the implications for computational emergence. Here's an outline of the talk. I'll review recent research results in the theoretical basis of modeling and simulation. The theory is yielding new insights into computational representations of complex real-world systems. And in particular, we'll talk about models that are constructed from iteratively specified components with well-specified input-output couplings. And I will explain what I mean by iteratively specified components, and that is the focus of this talk. In particular, DEVS, the Discrete Event System Specification formalism, is an instance of such iteratively specified systems. And this will lead to some implications for emergence and existence of systems where the theory provides existence conditions under which compositions of component systems form well-defined system of systems. And we'll talk about closure of classes of systems and system types under coupling, which also have implications for emergence. And we'll come to that at the end of the talk. General pattern of theory formation is that phenomena exist and somebody makes an abstraction, and then that person or somebody else eventually formalizes that abstraction, and that leads to some further development using the formalization, which is giving the rules and operations mathematical character, which eventually leads to real-world implementation. For example, Boolean algebra, which is the algebra that underlies propositional logic, was first brought to our attention by George Boole in the 1850s. And you could say that Boolean algebra, or the basic abstraction behind it being two symbols, 0 and 1, true and false, the distinction between just two very discrete entities, arose from informal reasoning and was abstracted in propositional logic, formalized later in Boolean algebra circuits, and then combined with the concept of threshold quantization, which converted real numbers into basically zeros and ones. To set the overall context of this talk, I'll use a notion of pattern of theory development that I talked about in another video, which is the idea that you have real-world phenomena, and somebody makes an abstraction of a phenomenon, and this leads later to somebody formalizing, bringing that abstraction into more of a logical or mathematical set of rules, and that eventually can lead to implementation in the real world of that theory or that formalization. For example, we can say that Boolean algebra eventually led to theories of transistors and microelectronic chips from a very simple start that Boole formed from the idea of an abstraction where you have two symbols, 0 and 1, or true and false, and some rules for manipulating them, which came out of informal reasoning as the phenomenon, and eventually got formalized in terms of Boolean circuits and the ability to convert electrical signals into zeros and ones through threshold quantization, which led to transistors and microelectronic chips and the whole technology of hardware that we have today. A similar kind of pattern of development can be recognized with the way that try to understand how people are working on arithmetic problems and algebraic problems using algorithms. We can identify that as trying to understand how one can do effective computation. Led to the idea of machine that represents how humans think, that Turing developed and was an abstraction, and that was formalized in several forms, including recursive function theory, lambda calculus. Eventually that led to programming languages, one of the first being the Lisp language, coming directly out of lambda calculus, and that eventually led to all our software currently today, with all its ability to program and do effective computation. So again, we have some real-world phenomenon abstracted in certain simplistic way and formalized so that it can be understood and manipulated, and eventually that leads to actual real-world application and implementation. Now I bring this up because I want to propose that this kind of pattern of theory development underlies the way that the discrete event system specification, or DEV's concept, emerged and became the basis for quite a large community of users in simulation. First, a little history. DEVS is based on Weimar's system theory. It describes both structure and behavior of systems and hierarchies of such specifications. It has components, component-based concept. We have atomic models and coupled models that are composed from atomic models, and these specify Weimar systems. And feature that will be particularly interesting to talk about later is closure of coupling, under coupling, which states that the result of coupling well-defined components, such as well-defined atomic models, is a well-defined DEVS, so that DEVS itself is closed under coupling. And this leads to hierarchical composition and a modular component-based approach to building complex systems, and also allows for dynamic structure where a model can change its own structure while executing. What's interesting too is that DEVS, though it's a discrete event, has a certain universality. First, historically, it was shown to be able to represent the different worldviews that were emerging from the simulation practice, where there were different ways of constructing simulation models. And these were all non-modular formalisms, in that they considered systems all as unitary and not decomposed into components that would be brought together, coupled into bigger systems. But DEVS included the ability to do that, and so it had a modular capability, and that was used to show the universality of DEVS, where all of the worldviews were included, but within even a larger set of classes. Now, first, a few words about the DEVS modeling and simulation approach. You have a system that you would like to simulate, and DEVS and system theory distinguish structural description from the behavioral description, where the structural description contains a hierarchical structure of the target system, and the behavior description contains the behavior, or how the system as structured behaves. And the DEVS approach allows to describe those separately but conjointly, and combine them to create the model that will be simulated to represent the real system. So we have both atomic models and coupled models. So atomic models have this kind of form. They describe the behavior of the component in a form that's not further decomposable, where there are state transitions and inputs and outputs. And the whole concept looks very much like a finite state machine, or a state machine more generally. But in particular, it's different because it has a time advance function, which says for any given state how long the system is going to stay in that state before making a transition to another state. So the system is now more event-driven than sort of a continuous evolution, because the system is in a state for a certain time. That time is dictated by its current state, and at the end of that time, a transition is scheduled to occur, and the particular new state that it goes into is determined by this internal transition function, and an output is generated just before that internal transition. Now, if the system gets an input while in a particular state, then it critically it takes knowledge of that input, the state it's in, but also the time that has elapsed since it got into the state until that external event occurred. And the three elements, those three elements determine the next state that the system will go to. And that makes all the difference in the world in representation power, because the devs' models can represent continuous systems, because you can replicate the course of or trajectory of a system from states at certain points. If you know the elapsed time, you can update the states to other points intermediate between the kind of known points. So this elapsed time is a unique feature of devs. It comes about because it was derived from the system theory concept of Weimar and others in the 60s. Now a quick look at how this pattern of theory formation can give insight into the development of devs. We saw that the pattern consists of a phenomenon, its abstraction, followed by formalization and implementation. In the early 1940s to 60s, computerized simulation, there was increasing amount of programming and using the early nascent machines to simulate real systems such as job shops and communication systems and manufacturing systems. And this was all done more or less ad hoc with machine language or developing kinds of programming systems. But there emerged a concept of event and event-based simulation and different forms of event-based simulation. And there was no real unified concept of what an event was, but that eventually happened with a concept of discrete event, and that was introduced by Katie Tucker in England in the 60s. But Tucker did not formalize that abstraction. He understood it and described it and used it in the basis for his developing of models of very complex steel plant systems, manufacturing systems, but didn't formalize the abstraction, which I did with the devs formalization. That led to the devs family of models and eventually to the devs simulation systems, which is the implementation that we're talking about in these times. Now, if atomic models are the essence of behavioral description, then coupled models are the essence of structural description. So a coupled model is built from atomic models that are coupled via input and output ports. For example, here we see two atomic models, and there's internal coupling in which outputs of one model are sent to inputs of other models, where this means that an output that is generated before an internal transition is immediately moved to become the input of the receiving model and triggers its external transition function, which behaves as we described, where it takes account of the current state and the elapsed time, as well as the actual input that was coming from the sender. There's also external input coupling, in which input ports of the coupled model are transcribed and distributed into ports of the some receiving atomic models, and also external output coupling, where outputs generated by atomic model components are fed, distributed to outputs of the coupled model itself. So notice that a simulator must be available that knows the rules and understands the semantics that we've just been describing to take these behavioral and structural descriptions to generate the behavior of the coupled model. Namely, when the atomic models are in certain initial states, then certain events will be scheduled, and these will lead to interactions among the atomic models, and these interactions will then lead to changes in state, and the whole cycle will continue. Continuing with structural description, we come to hierarchical Dev's coupled models, where we can do the same kind of coupling we just talked about for coupled models, but now with components that could be coupled models that we created just before we got to this stage, and atomic models that we have around. So the same kind of coupling will create more complex models out of parts or components that were constructed themselves from in a hierarchical manner. Now, this hierarchical construction is justified by the Dev's closure under coupling property, which says that a coupled model constructed by coupling of atomic models or of other coupled models is equivalent to an atomic model. But now the equivalence is in terms of behavior, and meaning having the same behavior or having the same form, interface, and dynamics as occur on the ports in the input-output behavior that a coupled model has in relation to an atomic model. Both can be equivalent, even though a coupled model has a different structure. Continuing with structural description, we come to hierarchical Dev's coupled models, where we can do the same kind of coupling we just talked about for coupled models, but now with components that could be coupled models that we created just before we got to this stage, and atomic models that we have around. So the same kind of coupling will create more complex models out of parts or components that were constructed themselves from in a hierarchical manner. Now, this hierarchical construction is justified by the Dev's closure under coupling property, which says that a coupled model constructed by coupling of atomic models or of other coupled models is equivalent to an atomic model. But now the equivalence is in terms of behavior, meaning having the same behavior or having the same form, interface, and dynamics as occur on the ports, the input-output behavior that a coupled model has in relation to an atomic model. Both can be equivalent, even though a coupled model has a different structure. As an example of the Dev's concepts I've been talking about, I'm going to discuss a representation of a Turing machine by Devs. It's an example of a unitary design or non-modular construction in a way it's usually formed, but what we're going to do is decompose it into simple components, a tape and a control, and we'll recompose them. We'll create a coupled model with simple coupling that will reconstruct the original in the sense of having the same behavior, be equivalent to it. This will give us a little basis for discussing emergence, because the components themselves are not that smart, but when you put them together, you get a device that can compute anything that any other computer can do. So you get the most that any computation can be done from such simple parts that are coupled together. This will also illustrate basic concepts of iterative system specification later on as we continue. So here's a Turing machine in both abstract and its physical realization. Turing created this abstraction to represent how people work when they're thinking. He conceived of a person's operations in their mind being represented by control and interacting with a piece of paper, or as much paper as they need, which is represented by the tape. And the control can only read a certain part of the tape at any given time. It can only read a square on the tape, which has a symbol either 0 or 1. And it can move the read head, so it can read different squares on the tape, but it must move the tape under the read head to get at a square. And these motions and moves left or right or stay in the same position are controlled by the state of the machine, and the state can be any finite number of states. So the state controller is limited because a finite state machine can't really do all computations possible. And the tape itself is pretty dumb by itself, but it has a very definite function, purpose that it can record and play back past scribblings of the human, that represents on the paper, and allow actually the computation to use as many states as needed. So even though a finite control has only a finite number of states, the tape extends that to an indefinite number of states as needed. So on the right we have the more abstract representation of the Turing machine with the tape as a square, a sequence of squares having zeros or ones, and a position, excuse me, a position of the readhead, where the tape control, TM control, can write a symbol and move the read head, and it can read a symbol on the tape at a certain position. Now let's look at how a composition of modular components can specify this kind of Turing machine. We isolate the components, the Turing machine control and the tape, and associate with them their inputs and outputs, where the control gets a symbol as input and produces a symbol and a move as output, and the tape gets the symbol and move as input and changes state accordingly and produces a symbol, namely the symbol at the location of its new location. So we can characterize each component as a Dev's atomic model, which I'll show you in a minute, and then we do a very natural coupling, which the Turing machine's output, the symbol and the move, are sent to the tape, and the tape responds, produces a symbol, which is sent to the control, and it responds, changing its state. And that coupling results in a resultant coupled model, which is a system that represents the behavior of the coupled model of the two components in the way they interact together, which should be equivalent to the original Turing machine. And this, we will show later, is a well-defined closed system composed of two open systems, and will be shown in devs. In this way, we can quickly show, using devs as the atomic models. We use set theoretic kinds of notations for the inputs, the sets, and the states, and the transition functions, and output functions, and time event functions, and so on. And tape system likewise. And then the coupled model is provided by the components together with the couplings that, as we've just discussed, take the outputs of each component, feed them to the inputs of the other component. And the dev's abstract simulator knows and understands what these symbols mean, this formalism means, and can create the trajectory of the global state transitions that represent the operation of the Turing machine itself. So let's return now to the concept of closure under coupling. First, with an informal meaning, let's say we have a concept of basic components and coupling so that we can have a assemblage of basic components and couple them together with external inputs, external outputs as well. And then we have a concept of coupled model where we can form a resultant system of these basic components, for example, a system of systems. And we're talking about now the resultant coupled model. And if we can show that it's equivalent to a basic model, not in structure but in behavior, then we would call that closure under coupling. But the resultant of the coupling of basic components is equivalent to a basic component itself. A little background on the history of a coupled model, closure under coupling. Wymore had shown that his systems were closed under coupling, although he didn't really emphasize that property. But when I define DEVs, the discrete event system specification, as a subclass of Wymore systems, or specifying such a class, and first in a classic form and then parallel DEVs, which allows more parallelism. I showed that was closed under coupling in both cases. And that supports hierarchical construction, as we saw, but also something called flattening, where the hierarchy is removed and only the couplings are retained, and that can lead to much faster execution because the paths for routing of messages, outputs to inputs are much reduced. But that closure under coupling also is what defines the abstract simulator for DEVs, because when you show closure under coupling, you in effect do a one-step simulation of the coupled model and show that this step can be represented by an atomic model in its functions. The hardest and most interesting proof of closure into coupling was done by Prayhofer in showing that the extension of DEVs, which combines it with differential equations that he defined as closed under coupling. This involved looking at all the various combinations of input-output signaling that's involved, and the types of components and the abstract simulator necessary to simulate such a component or such a model. It's all had to be brought in to prove this kind of closure and decoupling. So that is kind of the basis from which we start to consider the properties of closure and decoupling. This is the end of part 1. Please join me for part 2 under the same name in the next video.